Thank you very much. Hello, everyone. My name is Ming from the National Observatory of Athens. I'm working with Artisti Bonanos. So today I'm gonna talking about the involved massive star in the Magellanic Cloud. So first, I'm gonna give some general description about massive stars. So on the right side, you can see the typical HR diagrams. So above this dashed line, these are massive stars. So generally speaking, they have large initial mass, larger than 8 solar masses. They are relatively rare because of the initial mass function and also the short lifetimes. However, because of the intensive internal energy transportation and radiative output, they are connected with a lot of extreme phenomena in the universe, for example, supernova, black hole, gravitational wave, etc. And they are very critical for the stellar evolution, star formation, and also chemical evolution. And one of the important things for them is their mass loss rate. They play an important role in their evolution. And today we're going to talk about the massive star in the Magellanic Cloud. So why in the Magellanic Cloud? Because first, obviously, they are very nearby, so we can resolve individual stars. And second, they have different metallicity than the Milky Way. And also they are currently forming stars. So it makes a perfect lab to start an involved massive star. For my personal interest actually, I'm interested in resurgent stars on the HR diagrams. They are here. So they are like a hurting burning involved population 1 star. They are massive, they are very bright. They also have very low effective temperature and a relatively young age. And they are very big. So they are one of the very interesting targets in astrophysics. So when we're talking about the involved massive stars, one important thing is that they are very sensitive to the calculation of early evolutionary phases. However, any study of the involved massive star will require a complete sample, let's say, without the foreground contamination. But this is a general problem for them because, for example, Milky Way dwarf and giant, they may have similar brightness and colors as the Magellanic Cloud supergiants. So before that, for example, 20 years ago, it's very difficult to identify them because of the foreground contamination. However, now we have Gaia. And also because we want to start at the mass loss rate, the middle infrared data will be a very good start point. So we're using this spacer enhanced image product, which covers basically the main body of the Magellanic Cloud. And we first deblending the data, spacer data, and also the Gaia data, because we do not want too many blended target, which will influence our result. And we cross-match spacer data and Gaia data with 1 arcsecond to fix the position. So then it's kind of very easy to identify the member of Magellanic Cloud. For example, here on the bottom, you will see the 3 diagrams. The x-axis is the purple motion in RA deck and also parallax. Y-axis are their arrows. Obviously, you can see here there's a peak, 3 peaks here. So we just did the simultaneous Gaussian profile for it, and obviously, so from the on the right diagram, you see the purple motion in RA and DEC. Immediately, you see the clustering of the top member of the SMC. So here I take SMC as an example. So obviously, this method is very simple but efficient. So we approximately have 99.5% accuracy. So we almost identify every target as a SMC members. And After identify the members of the Magellanic Cloud, when we plot the color magnitude diagrams, you can see that a large amount of foreground contamination has been removed. So look at in the middle of the CMDs that this bunch of the foreground contamination are removed. So in total, we approximately have around 200,000 targets in the RMC and 45,000 targets in the SMC, sorry. And after have this fundamental source catalog, we also retrieved multi-wavelength data. So here we have more than 50 different filters range from the UV to far infrared. So in principle, it like we have a low resolution spectrum. So here shows you the spatial distribution of different data sets. So notice that we didn't cover the Magellanic Bridge, because if we do that, we will have also uncertainty about the distance. And once we have this multi-wavelength data set, the next step is very easy to identify the involved massive stars. Here, we're using MESA, isochron, and stellar tracks called MIST. So in the optical CMDs, we have 7 to 40 solar masses tracks cover the whole mass range. So we also have extinction about from 0 to 1 magnitude in V band. So basically, you can see from those diagrams, we are perfectly covering a large part of the blue supergiant, yellow supergiant, and also the red supergiant stars. So except using the MIST track, we also using theoretical color cat from Xioni and Boyer to specifically identify the red supergiant population. On the right diagrams, you can see these red targets. They are identified red supergiant stars by using the theoretical color cats. And in total, we have more than 10,000 targets. So they have been color coded as showing here, the different CMDs from Gaia and 2MAS. Here's the RMC, SMC. So the dark color indicates higher rank, which means that if one target has been identified in, for example, in 6 CMDs as the same type of involved massive star, it will be given as a highest rank because it's more reliable. And also I show here the spatial distribution. So you can clearly see this is a SMC. So you can clearly see the stretch towards the Magellanic Bridge because of the interaction between the RMC and the SMC. It's also a good indicator, means that our selection is correct. And after we identify a huge amount of involved massive star candidates, we also want to study the red supergiant in details. For example, here, we studied the red supergiant star in the SMC. So in previously, we only have photometric red supergiant candidates. Here, we also included some spectroscopy red supergiant stars because we did some constraint in astrometry and photometry, so you may lose some spectroscopy red supergiant star. And also the photometric candidates, they are selected in at least, they have been identified as a red supergiant star in at least 2 CMDs. So this sample is, let's say, more or less reliable. So we have 1,200 target, more or less. And the first interesting things, actually, we noticed that, so this is the zoom in of the CMD. So you can clearly see the population of the red supergiant star along this branch, or AGB stars here, the RGB population here, and also the tip of RGB. So from the diagrams, clearly see that we can more or less separate the red supergiant star from the AGB stars. And one more thing is that the lower limit of evolutionary track we use is 7 solar masses. So indicated by these dashed lines. And also we also see some targets along the red supergiant population, they are below the limit. That probably means the initial mass of the red supergiant stars can be lower as 6 solar masses, even maybe even lower. But we don't have, let's say, perfect model to identify them. And also the next interesting question is that can we clearly separate the red supergiant star from the HB stars from the previous diagrams? We do see some separation. However, can we really do this? So these diagrams contains a lot of information. I cannot go every details. So I just give you some simple conclusion that we have investigated the photometric data. So we see some overlapping. For example, here is the red supergiant stars and also the oxygen-rich AGB stars. They do have some overlaps here. And then we try to see if we can distinguish them from the spectroscopy. And unfortunately, due to the similarity of the spectral line ratio, there's also an overlap here in spectroscopy. And finally, we think maybe we can distinguish them by using variability. However, the answer is no. So our conclusion is that based on the current data, we actually cannot distinguish between the red supergiant star and the HB star since there's a similarity in the overlap region. And we also calculate the mass loss rate of the whole red supergiant star population in the SMC. So in the most conservative cases, it's about 10 to minus 6 solar masses per year. However, this is the most conservative cases. That means we probably underestimate the mass loss rate of the red supergiant star by using spacer colors. So why this is important? Because we have this missing dust mass problem. That means the maximum dust injection rate by the HB star and core collapse supernova are an order of magnitude lower than the dust destruction rate by the supernova remnants. So if we increase the mass loss rate of the red supergiant star, we may fill the gap. And also we also investigates the Geneva evolutionary tracks. This shows you about 20 years ago how it looks like, for the Geneva evolutionary track. So we can see obviously the red supergiant candidates are not covered by the tracks. But as the model improved, as the effective temperature scale improved, now we can better, we have much better coverage of the evolutionary track and red supergiant population. You may notice that we lack of brightest the red supergiant star. However, it's highly model dependent. You're using different bolometric correction, you may easily fill this gap. And we also have some outliers, but they can be perfectly explained by the variability plus also reddening. And the final interesting that we also found one of the most dust obscure target in the Magellanic cloud. So if you look at the middle infrared, the short wavelengths in the middle infrared data, it is actually very faint and red. However, if you moved, for example, 12 micron, it will be super bright and super red. So if you plot all the infrared data, middle infrared data in the, this target is from ARMC. So the target will be here, still very red, very bright. So it also shows the middle infrared light curve from NeoWise. It's a semi-regular variable. So probably it's some kind of super HB or the red supergiant star before the explosion. So this is my final summary. Thank you very much.
Okay, thank you very much, Ming. The floor is open for questions. You can raise your hand, write it in the chat, or just speak up. I believe anybody can unmute themselves and speak up.
Hi, can I ask a question?
Yes, please go ahead.
Hi, sorry, I couldn't find the raise hand button here. Yeah, hi Ming, thank you for a very interesting talk. I was wondering whether you have used the ETR3 data at all, because I think you've only not mentioned DR2, Gaia DR2, right?
Yes, I think those data are more or less. I understand that there's a improvement in the data set. However, they will be more or less the same. So maybe we will have like 1 or 2% of difference, but they are, let's say, they are almost close to the error bar because of the fitting.
Yeah, that's probably true as far as the colors are concerned, but not as far as the proper motions and parallaxes. So maybe your cutting, your pre-selection is going to change.
Yes.
Yeah.
I think the most important thing for my pre-selection is that we are based on the spacer and Gaia data. So as long as there's a data in spacer, then we select them. But however, not every star in the Magellanic Cloud has a spacer data. So
true. So that was one sort of comment, more or less. The other question was about the models you are using. I heard a talk very recently saying that from comparison of synthetic models with various data from galaxies and so on, they found that the mixed isochrones are not as good as the Padova ones, the parsec ones. Have you considered using the parsec isochrones at all for your work? Or do they not cover the masses you're interested in?
Yes, actually, that's the first thought I have for the RMC data, because you are right. For the RMC data, for the RMC metallicity, the missed track, they have problem, because I found this problem. So I contact with the author. He told me that they will update the models. However, they haven't finished it. And also Padova data, Padova track, I also connect, let's say I also talked with people from Padova. The problem for their model is that they didn't including the rotation.
Yes.
That's
so
one of the.
Now I think, that's
they are actually building now, I think, But when I did the job, they didn't finish the job, so I cannot use it.
Yeah, you're quite right. Yeah. Okay, thank you. Thanks, Ming.
Thank you.